Yes, welcome back, Professor Gillian Roehrig and team. Steph Erickson is already here. And should we also wait, Betsy, or we can start now?
We can go ahead and get started.
Yep.
Unfortunately, Betsy will not be able to join us this evening.
Uh-huh.
She tested positive for COVID early last week, and she's still having some symptoms. So it's just me and Stephanie tonight.
Okay, good. Thank you very much. Hello. Welcome back, Steph. And now we are ready to go to the second week of workshop together with Professor Gillian Roehrig and also Stephanie Erickson from University of Minnesota. Now I give the time for Master of Ceremony to start the workshop, please.
Okay, good morning, everyone, ladies and gentlemen. How are you all today? Okay, nice to meet you again in today's workshop. We would like to express our gratitude and welcome once again to the Honorable Head of Science Education Department, Dr. Paet Norma Yunita Indrianti, the Honorable Speakers from University of Minnesota, United States, Professor Dr. Gillian Roehrig, and Ms. Stephanie Erickson. Teacher as invited guests, and students of Universitas 11 Maret. First of all, we are grateful to our God Almighty because we can gather again in today's meeting and without any obstacles. Today is a great honor for me, Salom, to greet each and every one of you to continue the event. We proudly continue the workshop on STEM that has started from last week. The next agenda is continuing the interesting presentation session from last week. We are grateful to have Professor Dr. Gillian Roehrig and Ms. Stephanie Erickson. Please get ready and stay focused on the presentation. The same as last week, this session will be moderated by Ms. Febriani Sarwenda Asri N. Ms. Febriani Sarwenda, the stage is yours.
Hello, good evening, Professor Gillian and Stephanie. Nice to see you again here. So the same as last week, I'm the moderator of this session. And we have time until 11 here. So the time is yours. And then after you presenting, and when we have activity to do together, I will translate it to the participant here. Okay, the time is yours.
Thank you very much for your kind introductions. And again, apologies from Betsy. She's really not very well. So she sends her apologies and she is sorry to miss you all. So I'll also let you know there's quite a big thunderstorm going around me here. So if you hear some banging, it's thunder. So hopefully my connection will stay okay here. So, all right, I'm going to get my slides up here so we can go ahead and get started. Let's get it on slideshow so it's easier for us to see. All right, so we're in day 2 of our workshop. And so just briefly our agenda for today, and we'll do some refreshers from last week, just sort of remind us what we covered and connect us to where we're going today. And then you'll actually get a chance to engage in the engineering design activity. So we'll actually get to think about how we're going to save our penguins. You won't be able to actually build something, right, with the online piece, but we'll take you through that so you have an experience of what it might feel like for your students. And then once we're done modeling the Save the Penguins activity, we'll reconnect to our integrated STEM frameworks and think about some of those important characteristics of STEM and how the activities that we've done have modeled some of those and ways that you might think about using some of these strategies in your own classrooms. So last week, as we walked through the frameworks and really focused ourselves on the engineering design cycle. And so as a reminder, I've got an image of the engineering design cycle here, right? So as a reminder, we start with defining a real world problem. What is it that the client needs us to do? A new process, a new product to solve a problem. We then learn the relevant STEM content that we need to be successful in solving that problem. And then we move into planning a prototype and iteratively trying and testing that prototype until we're able to make a final decision at the end about a possible solution that would meet the client's needs. And so with the Save the Penguins curriculum, we worked a little bit on define last week. And so briefly, the problem that we were looking at is how can we better support the penguins on Boulder Beach in South Africa? And how can we use our knowledge of heat transfer to design, build, test, and evaluate a habitat that could help keep the penguins cool? And if we can keep the penguins cool, they're going to sit on their eggs properly, and they're more likely then to hatch a healthy baby penguin. All right. And we'll come back to that problem in a little bit more detail as we move through, but just a quick reminder of our problem that we were looking at. And we started Learn last week, right? We did some science lessons. There are a series of 4 lessons that are in the curriculum. And we did quite a bit of work on heat transfer and insulators. So Stephanie and Betsy took you through the example with the cans, and we learned about how different materials have different insulating properties. And if you remember, the wool sock and the paper towel were our better insulators out of the set of materials that we had available to us last week. And we thought about the properties of those materials, how they have a lot of small air pockets, and those air pockets are able to trap the hot air and then slow down that transfer of the hot air into the can. All right, so we did some thinking about that. You did some work on Jamboard with that, which was great to see you starting to think about those concepts and how you could explain what was happening in a visual. All right. So what we'll do briefly to kick us off is we'll take a quick look at conduction, convection, and radiation, just to make sure that it's really fresh in our minds. I'm sure this is science content that you've had somewhere in your teacher preparation program, but just to make sure that it's really activated for us. And we won't spend as much time on it as we did. We won't do any Jamboards with this because I want us to spend most of our time today on thinking about the engineering parts of that. All right. But I do want to make sure that we have that science content so we can apply it. So I just want you to imagine at this point what it would feel like. So if you had a metal spoon and a plastic spoon and you were to hold them to your cheeks or somewhere on your body, about what it would feel like. Okay. All right. And as you think about that, what you'll feel is the metal spoon is going to feel colder. Okay, you're going to feel that cold on your cheek compared to the plastic one. All right. And when we ask students about this, they'll often tell us, well, the metal spoon is colder than the plastic spoon. All right. And part of what we have to think about here is if we have any 2 objects in the room, I've got my iPad and some different things here, right? They're all in the same room. They're all the same temperature, right? Right. I'm probably at about 20 degrees, right, Celsius here. All of the objects in the room are at 20 degrees Celsius, but the metal spoon feels colder to us. All right, so what we would do at this point is really engage and think about, well, why is it that the metal spoon feels colder? All right, what I'd like you to do is just take a couple of minutes, turn and talk to your group members, and come up with an explanation for why is it when we hold the spoons, why does the metal spoon feel colder than the plastic spoon? So I'll give you a couple of minutes to talk about that and activate some of your ideas.
Oke, Bapak, Ibu, dan adik-adik, di sini ada pertanyaan. Di situ ada 2 sendok. 2 sendok, satunya dari besi, satunya dari plastik. Pertanyaannya Prof. Gillian adalah, jika keduanya diletakkan di dalam ruangan yang sama, mana yang akan lebih terasa dingin ketika ditempelkan di pipi, dan mengapa demikian? Silakan didiskusikan. Jika ada yang ingin berpendapat, monggo. Dijelaskan ya, kenapa terjadi demikian. Professor Roehrig, do the
Yes.
student need to present the result of the discussion or not?
It would be wonderful if we could ask one group to share their ideas. That would be great. Thank you.
Okay.
I'm very proud of all of the students in the room for being willing to step up and share their ideas. So.
Yang ingin mempresentasikan, silakan.
Is there a group ready to share?
Oke, Bapak Ibu, adik-adik silakan yang ingin share, raise your hand please and come to here. Yeah, come to here. Raise hand. Yeah, come here. Okay, Arinta, come here. Please introduce your name first.
Hello, Prof. My
Hello.
name is Arinta. I wanna answer this question. Why does the metal spoon feel colder than the plastic spoon? Because metal spoon is a good conductor. So when I hold the metal spoon, the metal is pulling heat from my hands and giving them the feeling of being cold. Okay.
That's a great explanation. Thank you, Rinda. I appreciate that. Right. So we're still thinking about. Thank you. Thank you.
We have one more participant here.
Okay, wonderful. We'll take another one. That's great. Thank you.
Hello, Prof. My name is Juwita Dewi.
Hello.
I'm from Group 9, and why does the metal spoon feel colder than the plastic spoons? Because the metal spoon is a good conductor of heat. That means when the object is affected to an iron surface, the energy of the object is immediately absorbed by the metal spoon. So when we hold the metal spoon, the energy of our skin is transferred to the iron. So our skin lose some its energy and our skin feels cold like that. Thank you.
Thank you. Some great explanations. Thank you to the two students who shared, right? So I can hear you using some of our vocabulary words, right? I can hear the word conductor, right? The idea that the metal is a better conductor than plastic, and that because of that, it's better able to, we get better heat transfer or energy transfer, right, from our face into the spoon, right? And what we're feeling on our face is actually that absence of heat as it's been transferred into that metal spoon. All right, so wonderful explanations. So for our students, we would introduce then some new vocabulary words. So conduction, and we talk about conduction as a simple definition, right? It's dependent on the age of the students that you're working with. You might use a more complex definition, but as a simple definition, we think of conduction as the transfer of energy by direct contact. So for heat transfer to occur through conduction, there has to be touching, right? I have to, like, two objects have to be in contact for heat to transfer, right, between the cell phone in this case and my hand, right? There has to be direct contact for that to happen. All right. I'll just talk you through this one. But what we have the students then do to really reinforce this is we have them do a really, really quick experiment, and they take the plastic spoon and the metal spoon and they hold them with an ice cube in each of the spoons. And we ask the students to make a prediction which of those ice cubes is going to melt fastest and why do they think it will melt the fastest. And then it doesn't take more than a few minutes of holding those spoons for them to be able to test that prediction. All right. And using the ideas that the two students just presented, right, knowing that metal is a better conductor than plastic. Metal is better able to transfer the heat from my hands through the metal spoon into the ice cube, right? So we would expect that the ice cube in the metal spoon is going to melt faster, right? So this is just a way to really reinforce that idea for students. All right. So this one I will have you turn and talk with your table. And so we're going to look at two new ideas with heat transfer, convection, and radiation. All right. And so I want you to imagine that you're in your house on a hot summer's day. And I want you to think about, why is it that it's hotter when you're in a top floor of your house, right? We call that an attic, right? So when we're in the top floor versus in the basement, all right? So turn and talk with your group about why do we feel warmer on the top floor of our house in comparison to the bottom floor of our house. And we'll ask for one or two students to share their ideas here. All right, so turn and talk to your neighbors, take a couple of minutes, and then we'll take some comments from the floor. Okay?
Oke. Oke, ada pertanyaan kedua. Ini pertanyaannya, bayangkan sebuah rumah pada musim panas atau musim kemarau kalau kita, kenapa lebih dingin yang di basement atau yang di bawah, yang di bagian bawah, bagian ruang buat tanah, daripada yang di atas atau yang dekat dengan atap? Oke, nanti satu orang silakan angkat tangan dan share jawabannya kenapa demikian. Satu orang yang paling cepat angkat tangan, nanti silakan ke sini dan membagikan atau memberikan penjelasannya. Ada yang sudah siap membagikan jawabannya? Please raise your hand. Ya, Bu Guru boleh. Siapa saja peserta di sini boleh. Please. Yeah, you can speak also in Bahasa Indonesia and we will translate it for Professor Gillian. Yeah, please. Silakan Bayu. Okay, we have one participant who want to answer, Prof. Gillian.
Thank you.
Aku belum nyiapin skripnya.
Ya, jadi sorry, Miss, I use bahasa in Indonesia, will translate Bu Sarwenda.
That is okay.
Sarwenda. Ya, jadi intinya adalah ketika cahayanya sudah masuk atap, itu atap akan menyerap radiasi dari panas mataharinya secara langsung, sehingga radiasi dari yang lewat sampai ke basement itu udah diserap atap. Itu kalau secara radiasi. Sedangkan kalau secara konveksinya, ini ada kaitannya sama udaranya, di mana kalau si atap itu udaranya nanti akan semakin memanas. Nah, terus nanti yang di basement itu kelembapan udaranya akan semakin dingin karena ya tadi radiasi mataharinya tuh nggak sampai ke bawah. Mungkin intinya gitu, Bu Sarwenda, monggo ditranslate.
Okay. Let me translate it for you. According to our participant, Bayu, why the attic of the house will be a hot place in summer? Because the direct sunlight from the sun will get into it directly by radiation, but in the basement, the radiation is not come to there, or it is far away from the attic, and then the basement will be get more moisture, so the sunlight from the sun is not come to there.
Okay, there's some interesting ideas there, right? So for us in Minnesota, we have a basement. I can definitely say our basement is moister. And we get a lot more condensation there, right? And there is no direct sunlight, right, hitting our basement. So there's definitely some factors there that are part of that problem, right? And we'll talk a little bit on the next slide about radiation. But what I want us to think about a little bit here is convection, all right? And so when we think about heating up our house or cooling our house,
I'm sorry.
Right? Here.
Professor Gillian, we have one more participant who wants to participate.
Okay, excellent.
Yeah,
Thank you.
it's good.
I'm sorry. It's very hard when I'm not in the room, and I love to talk.
I'm sorry. I try to speak English language, but my English language not friendly.
Your English is a lot better than my Indonesian.
Yes. My name is Sri Supati. My name is Sri Supati. I come from Union High School, One Karanganyar. My answer may be the same with Mr. Bayu. Maybe. On a hot summer day, the attic is hotter because the attic got radiation of sun, and then the basement colder because in the basement may be many things in the basement to save energy and then become colder.
Thank you.
That's all, Professor. Thank you.
Thank you. Thank you very much. Right. So we've got two different ideas here, right? Right. One is about radiation. All right. And then the other one that I'll add in a little bit is about convection, right? So the reason that our house is getting warm on a summer's day is, and I heard both of the presenters say this, is about radiation, right? So the heat from the sun is reaching us right through waves, heat waves, right, and is started to warm our house up, right? So radiation is definitely a factor in why our house is getting warmer, right, on those summer days, right? But we also have another thing that's happening here, which is called convection, and I'm actually going to jump to a different slide here quickly because it might be easier to illustrate here. You can see convection here. This happens to be in a fluid, right, in water here heating up, right? But when we heat water, right, and we're heating the bottom there of that pan of water, you start to create these convection currents, right? So we think about the change in density as we heat up the air. So if I go back to my house here, there'll be a shift in density as well, right? So that hotter air is less dense and is going to rise to the top of the house, and it's going to push down that colder air, which is more dense. So as well as the radiation that we have happening, we also have convection, right? So as that air, the hot air rises and pushes down the more dense cold air. So we also have convection currents in our house. That adds to this this issue, right? So it's going to be hotter at the top where the air is less dense, and colder at the bottom where we have that more dense air. All right, so we have convection currents happening as well as that radiation from the sun. Okay, so one of the second form of heat transfer that we want to think about is convection. So that movement can happen either in a gas or a liquid. And for us in our house, it's the gas, it's the air that's in our house. And when we have convection, the warmer parts move up and the colder parts will move down. All right. So we also have to think about convection as a way that heat moves in a large space. All right. In my example, in the house. Okay. All right, with radiation, which the groups have talked about a little bit, so I'll just talk a little bit about this one, and then we'll move on to our engineering piece. When we think about that radiation, right, and both of the presenters talked about that energy from the sun coming as radiating and hitting our house and warming it up. All right. And so when we think about ways that we can prevent that radiation, all right, one of the things that we think about is how can we keep our house cooler, right? That's something we don't want to spend a lot of money trying to cool our house, is thinking about putting some kind of reflective material on our house. So if I was to cover my roof with something reflective, I could start to prevent that heat transfer by radiation. I could reflect that heat away. And so radiation is that third form, which each of the groups talked about, which is the transfer of energy in the form of electromagnetic waves. In almost all cases for us, right, the main source is going to be the sun, right, that provides that heat. But we have other sources in our house. I'm sitting next to a lamp here, right? There's heat coming from that lamp that's radiating that I can also feel when I put my hand close to the lamp. All right, so we've also got convection and radiation that we need to worry about. Okay. All right. So, and then this slide that I jumped to quickly when I was talking about convection is just to sort of summarize those three kinds of heat transfer that we're going to need to think about when Stephanie talks to us a little bit more about designing those penguin habitats. All right. So we've got conduction that you can see here. So that's by touching. So if I have a metal pan of water that I'm heating up, I'm going to boil some water. If I grab the pan, ouch, right? That's hot, right? I'm going to feel that heat radiate, conducting into my hand. All right. Okay. I actually don't need to put the pan right onto the stove because that heat will radiate from the bottom. All right. So if I put it down, I can get conduction. If I'm just holding it slightly above the heat, right, it will still radiate and I will get heat transfer that way. All right. And then that last form is that convection, those currents that we can get in a large space where we get the movement, the change in density of the hot and the cold fluids. Okay. All right. So what I'm going to do at this point is I'm going to pass things over to Stephanie. All right. So we've wrapped up our learn phase. All right. And she's going to reintroduce us to our penguin problem and start to walk us through the engineering piece. What I'm wondering here is, I don't know if you want to stop and translate anything I've just said. I will warn everybody as Stephanie starts to explain this. It's a lot easier when we're in the classroom and we can hold up materials and you can see things. So it might be good, Stephanie, maybe if you want to stop at a couple of points so we can get an Indonesian translation so people are able to follow all of the different materials and things that they're going to need to keep track of. Okay, so I will keep moving the slides for you, Stephanie. I'll mute and let you take it on. Okay.
All right, thank you. So exactly what Professor Roehrig just explained is we're going to try to simulate and go through the engineering design process that we would have students go through in a classroom, but modified because of our Zoom and distance situation. So just to remind you, last week we had these penguins that were getting too hot and the parents needed to cool off in the water and they were leaving their eggs behind. So what we want to do is save our penguins. That's the name of this curriculum. And we want to have the parents be able to stay next to their eggs and protect their eggs and keep our penguins cool. And so we're going to design a habitat. We're going to make a prototype of a habitat that will keep our penguins cool on these hot beaches in South Africa. The next slide. So we've got, if we were going to have you do the building process, we have a variety of materials for you to use. And you can see what those materials are in that picture. That's what would be available in the classroom for you to use to build your habitat. And we're going to simulate that using an ice cube. So your penguin is going to be this ice cube, and we're going to try to keep the ice cube from melting and make a little habitat for our little penguin ice cube. So you will see that these are the materials that are available, but you can't use them all. You have to, we don't have unlimited money. So you're going to need to think about what materials you're going to want to use so you don't run out of money. And you have to stay within a budget. And we'll give you some information on the materials and how much each material costs in a couple of slides. All right, next slide. So we're going to go through a, this is an experiment that we would have students do and design and test out some different materials in their box. So we would have students designing an experiment. They would go and collect some data on the starting temperature and the temperature after 5 minutes to kind of explore what materials are better than others at keeping that ice cube from melting and keeping that penguin cool. So we've got foam material, aluminum, mylar, which is kind of like aluminum, but a little bit fancier. It has that reflective quality to it. Paper of different colors, felt, which is kind of like a fabric, kind of like a wool fabric of different colors, and bubble wrap. So I think we're good on that. Next slide.
I just wanted to check, make sure
Yes.
if there's any questions about how this data would be collected, because we won't have the opportunity to do that, obviously, as a group. Just want to make sure everyone's okay. All right. Okay. If there are questions, just stop us and let us know, because we're very aware that we're giving you a lot of information without you being able to see and touch the materials. So.
Okay. So we have students do this experiment, and this is the data they found. And this was done in the United States, so using the Fahrenheit system. But Jill, if you could use your pointer to that last column. The main thing is which one warmed up the most and which one seemed to keep our penguins safe and not have a lot of temperature difference. So, it seems here our aluminum is the really good one to go with. It didn't have a very big temperature change, but our black felt didn't do so hot. It didn't do a very good job at keeping our penguins cool and keeping them next to their eggs. And and that has to do with aluminum. Maybe has that reflective quality, so it's there's less radiation coming in, and black, that color tends to maybe absorb some of that energy from the sun and heating it up more. So color seems to matter here, and being able to reflect light seems to be important too. All right, and we have some more data here, this time in Celsius. But again, it's that change in temperature that is really important, that we want to care about. So we have the aluminum again doing a really good job. And then aqua might not be a word, that's blue, kind of a light blue color. And that did an okay job. And then the yellow foam did a pretty good job too. So it seems like, you know, foam and felt seem to be doing okay, but the color matters. You know, how much energy from the sun gets absorbed by the different colors is important. So, and then the bubble wrap, we talked about those air pockets in the wool in our socks and our cans. So the bubble wrap kind of makes those little air pockets. And there was, you know, it's kind of in the middle of ability to keep our penguins cool. I'll pause again to see if there's any questions about the data. You'll be able to see this information on your Jamboard too. So as we move forward, you'll be able to refer and look back at these numbers. But are there any questions about these numbers and what they mean?
Bapak, Ibu, atau adik-adik, apakah ada yang mau ditanyakan di sini tentang apa yang dijelaskan? Ini pematerinya menjelaskan bagaimana macam-macam bahan yang digunakan untuk menjaga es. Tadi kan mau membuat sarang penguin ceritanya. Nah, dari membuat sarang penguin itu, penguinnya diibaratkan sebagai es. Dan kemudian di situ ada berbagai macam bahan, tempat naruh esnya itu supaya dia tidak meleleh. Di situ ada beberapa, ada warna-warna yang berbeda dengan bahan yang sama. Hasilnya di sini bahwa dengan bahan yang sama dan warna yang lebih gelap, delta T atau perubahan suhunya itu lebih besar. Itu intinya di sini. Apa ada yang mau ditanyakan atau jelas? Materialnya, jenis bahan-bahannya tahu? Tahu. Tidak ada pertanyaan berarti? Tidak ada pertanyaan? Okay, it's all clear. You can continue, please.
Awesome. Okay. So we're going to have you think about and design a habitat, draw it instead of build it. We would have the students drawing and building, but we're going to have you think and draw. So as you think about your design that you want to use, these are the materials that would be available to you. But you know, some materials are more expensive than others, and you only have $200 to spend on your habitat. So you can't use all of the materials. Mylar has a really good reflective ability and performs really well, but it is also very expensive to use. But aluminum foil is cheap and, you know, does a good job. So when you're thinking about what you're making your habitat of, you need to think about not going overpriced. And so you only have $200 to spend on your materials. So you don't get to use all of your materials. And so again, we will have this available for you to look at when you go into your design process. So you can look back at both the prices and the performance of these materials. Next slide. So here is our hot simulated beach, our South African beach where these penguins live. we've created this cooker. We've got 3 hot lamps pointing down into this box, and this box is lined with aluminum foil. So that light is reflecting down into it. And I'm trying to remember, and the bottom of it is black. So this thing is designed to get really, really, really hot. And the test environment then of our little ice cube penguins is you're going to put them in the habitat, and then we're going to put them in the box for 20 minutes to see if they melt and how much they melt. Because they will melt. We're just going to find out how much they melt. And the goal is to have the least amount of melting for your penguin. So this is where we're going to be putting our penguins, is in this really, really hot box. Okay, so what we're going to do is go through the prototyping portion of this engineering design unit. This is what we would call the plan phase. And this is the part we're going to have you do. And we're going to give you 20 minutes total to do it. The first 5 minutes, we just want you thinking by yourself. So first 5 minutes, you're not talking, you're just thinking, drawing on a piece of paper what you think you should have. And then we want you, after you've had time to think by yourself, we're going to have you get together with your group, share everybody's ideas, and then each group is going to put their design on their Jamboard. And that Jamboard from the group, we want a picture, a visual, and it would be great if you could label your pictures, like this is aluminum, this is black foam. And then we also want a written sentence that what we would say justifies your decisions. And we've given you a sentence starter there. We choose to use blank because blank. So tell us why you use those materials. So labeled picture plus sentence explaining why you use those materials. And we're going to give you 20 minutes. And at the end of the 20 minutes, we'd like to see, something on the Jamboards from each group. And now I'm going to pause and let you translate all that.
Could you please copy the link to the chat, please?
Yes, I will. I'm getting the Jamboard right now.
Oke, Bapak Ibu, tugasnya sama seperti minggu lalu. Jadi ada tugas sendiri, tugas mandiri, seperti tadi, membuat rancangan yang menurut Bapak Ibu yang paling cocok, bagaimana membuat supaya es yang di tengah tadi itu tidak meleleh, meskipun ditaruh 3 lampu yang suhunya panas. Silakan dibuat rancangannya sendiri. Naruh esnya seperti apa, bahan yang di samping-sampingnya yang untuk menjaga itu seperti apa. Kalau tadi contohnya menggunakan aluminium foil karena paling murah dan paling efektif. Kemudian itu hanya 5 menit waktunya. Setelah itu nanti 15 menit terakhir silakan dibuat rancangan kelompoknya mirip seperti itu, tapi bisa digabungkan ide-idenya. Jadi ke konsensus kelompok. Jadi mau yang seperti apa sih desain kelompok kita dalam bentuk gambar, dan juga ada tulisan katanya tadi, misalnya ada konveksi, ada konduksi, ada radiasi, kenapa ditaruh itu di situ, seperti itu. Nanti akan di-share, di foto saja, masukkan ke Jamboard seperti minggu lalu. Jadi waktu bekerjanya 20 menit ya, untuk individu 5 menit, menurut masing-masing bagusnya gimana. Setelah itu 15 menit diskusi, konsensus kelompok, mana yang mau kita pakai atau mau menggabungkan yang seperti apa. Nanti kemudian ketika menjelaskan di Jamboard-nya kan ada presentasi di akhir 20 menitnya ini, kenapa memilih desain itu, tunjukkan gambarnya, tunjukkan teorinya atau kata-kata kuncinya dari Bapak Ibu kenapa memilih itu. Alamat Jamboardnya ada di chat, sudah di-share ya? Nah,
So
sudah
when
di-share di grup.
you get into your Jamboard, the first page will have those tables that Stephanie shared with you with the data and the budget, so you'll be able to easily refer to the information that you need, and then you'll find a page for each of your groups to do the work. So as you need that information, it's on the first page of the Jamboard. Okay.
Di Jamboard sudah ada data harga bahan, ada kemampuan menahan panasnya atau menyimpan suhunya, itu perubahannya supaya tidak terlalu jauh. Nah, itu silakan dimanfaatkan datanya, mau menggunakan yang seperti apa. Tapi tadi maksimal budgetnya hanya $200.
Okay, so we're going to give you those 20 minutes to plan and sketch out. If you have any questions, feel free to ask. We are here to answer any questions. But right now, we're going to give you the time to work with, first think yourself and then work in your groups for the next 20 minutes. And then we'll come back together.
Oke, jika ada yang ingin ditanyakan, boleh. Akan kita langsung tanyakan supaya mempermudah jika masih ada yang bingung.
just going to give a time update. Got about 10 minutes left. And we want to start seeing some pictures on our Jamboard using the materials listed. So on that first page, we want to see some pictures of those materials and then labeled using the materials on the list. So about 10 more minutes.
I'll just share briefly on the screen just an example, not to copy, but to give you an idea of what we're looking for. So I'm not going to keep this on the slide on the screen for too long, but right. So you've got a picture showing what your design would look like, explaining your materials, thinking about your budget. Okay, all right. Just to give you sort of an idea as to what this might look like. Okay. I'm going to take them off because I don't want you copying any of the designs, but just to sort of give a visual about the drawings.
Okay, we're going to give you 2 more minutes. We are looking at the Jamboards and seeing that many groups are just putting their ideas down. So we're going to give you 2 more extra minutes, but take that time to just get your ideas. If it's a picture of a hand drawing, that works too. All right, so if we can come back together and maybe turn our bodies back to the front, and we are going to go over some of these designs that we've come up with. Yeah. Okay, I'm just kind of looking in the room. One of our squares, we can see the room. So I'm just kind of looking in the room to see that we are all back together. Looks like most of our groups were able to put something on the Jamboard. So we're just going to go through. In the classroom, we would have students talk about their design ideas and share their ideas out. With the idea that it's not a competition of who's the best design, but to learn from each other's design ideas. So we're going to share out, but for time purposes and for this environment, I'm just going to go through the designs and highlight some different design ideas that maybe your group could say, oh, that's a really great idea. I think we can use that in our design too. So we're not meant to be a competition, but to share in our community different ideas. So our first group here has their budget up here. It looks like, doing my quick math, they're pretty close to their $200 budget. They've got their penguin inside this box, surrounded by some white foam, some aluminum foil. Looks like they're making some air pockets out of the paper baking sheets around the outside. They've used some of our vocabulary words with reflection, so that outside aluminum foil is reflecting some of that light away and that energy away. The radiation is coming in from here. Yeah, so they've got that air cavity here. And then the aluminum foil didn't, was able to block a lot of that heat. So they decided to use that aluminum foil design there. And they have a very cute little penguin drawing in here. Penguins looking pretty happy and protected inside our box. Group 2, they came in with a whopping $84 for their penguin design. And they're protecting quite a few of penguins here inside their box. Even with their budget of $84, they decided that the Mylar was worth paying for because of its ability to reflect some of that light. They put it at the top. They put some aluminum foil in there, some craft sticks. Maybe for some stability and for some structure to make the house. And then some air pockets from the bottom. So that heat coming from that black bottom, maybe those air pockets were helping it, keep our penguin cool inside with that bubble wrap. So they used some expensive material, but they still were able to get an $84 budget. Group 3, another low budget, $44. I think this is our new low budget winner, where they have their penguin inside of a box surrounded by yellow foam. And then they say in the writing that there's also some aluminum foil around the outside. So really went simple, aluminum foil on the outside, some yellow foam in the middle, and then put our penguin inside this box. Let's see, group 4 is adding things as we talk. Coming in comparatively at a pretty high price of $126. They decided to use that Mylar, go with that expensive material and use that Mylar on the outside. Have some blank space inside. So they're starting to think about these air pockets and how much blank space should be inside there. And they've got some aluminum, some white foam inside there, and using some of that foam as an insulator, and kind of thinking that as that foam is maybe a lot like styrofoam that we use in our coolers. Basically, their big idea was to make it a lot like a thermos. So this group is bringing in some of that everyday experiences. We want students doing that. We want them to think about, hey, I use a thermos. I happen to have one in front of me to keep my beverages cold or to keep my beverages hot. I bet we could do the same thing to protect our penguins. I think that that is what we want our students to do. And as teachers, we want to bring that out of our students too when we do these engineering designs. So I like that this group added that thermos idea. And now we've got a cooler, kind of a styrofoam cooler. So we have group 5 coming in with a budget of $184 because they're using a lot of white foam. So they're making like a cooler made out of white foam to keep their penguins safe. And then they've got some aluminum foil lining the inside. And my screen share, I can't see. Oh, and they're wrapping the box with light felt. So they are kind of doing a 3 layers in this box around our penguin. And here, group 6, $40. So this is kind of coming in on our low end here, where they're just wrapping it up in a foam sheet. So using one foam sheet and wrapping it up. Group 7, group 8, another $40 prototype. Kind of a couple different pictures. I love this is, I believe, the penguins from Madagascar, the movie. Reminds me of my children. They loved that movie when it came out. So I like seeing that guy. And then we have another penguin in here who's pretty happy inside the craft stick house with some baking cups to make some air pockets around the penguin and some craft sticks to make the house. And showing that there is kind of some heat coming from the bottom here that we don't even need to think about the sun beating down, but that hot sand. And in our box, that black bottom that we need to also protect our penguins from. Group 9 coming in with $94 price. Using that bubble wrap for some air pockets. Oh, the first time are you seeing the cotton balls being used as kind of a protective layer around, I believe this is going to be the penguin, and some paper cups for some air pockets again. But new material being used is some cotton balls. We're not really seeing that bubble wrap used very much either. That might be a cost decision that was brought into that. And finally, group 10, used some foam and some aluminum and just kind of made a little bed for our penguin. And coming at a cost of $88. But could look for some reasons, but group 10 now has seen 9 other groups to see their reasons and can learn from those groups. Can say, oh, you know what, we decided to use the foam because it was really good at insulating. The aluminum foil because it was good at reflecting the light. So the reason we share these ideas is for others to learn from each other. So now group 10 can go back and maybe have a reason that they can write about that they saw in other groups. And I think that's it. Oh, no, that must have been that other group. And then now we have group Neural and Friends coming at a cost of $100. And we have an aluminum foil and some white foam, and then our ice cube penguins in the middle here. So a lot of white foam being used, a lot of aluminum foil being used, and some people thinking about that Mylar and willing to spend that money on that Mylar. So I'm going to go back to our slides here. Or there we go. Jill's got them for us. So there is no perfect design. And we can now kind of think about, well, which one do we think is going to be the best one and why? And we have some. This is some work that we did with some students here in the United States. We had them come up with fun names for their teams, like Funky Chicken, Frank's Fries, Oreos. Oreos are like a chocolate cookie that are really, really good. And they came up with their prices. Looks like their budget was a little bit more than $200. And then we kind of highlighted the ones that were kind of the lower cost, but we want to balance that with, did it actually work? So we could have a really, really affordable design, but if there's too much melting of the ice, that's what this mass last is that we want the lowest amount of mass change. So yeah, we're looking at what is being highlighted right now with our melting penguins, but it's pretty expensive. So we need to balance that with the cost. So this is kind of the testing phase. where we put it in the thing and see how much was melted. And we would have the students do this multiple. So we'd have them build it. We'd have them put it in this hot machine, this big box. So this first one we're showing had 5.5 grams remaining, and the one on the right had 7 grams remaining. So that means the one on the right had more ice left over, which means it was better protected and stayed cool better. And so we want students
Stephanie,
to do,
these are so the one on the left is their first attempt, and then
thank you.
using the data that they collected, the one on the right is their redesign.
Thank you.
Yep.
Yeah, so we want students to try it first and then go back and redesign. And think about, are there materials that they don't need anymore? Are there new materials that would work better? So here it looks like they made their pocket and their little home for their penguin a little bit smaller, and they added another foam layer to it.
I think the other change, Stephanie, is that they've lifted this off of the floor just a little bit, right? So in their initial design, the habitat is touching that black bottom, so there's a lot of conduction, right, of heat from the bottom. And so one of the there's other changes as well that you noticed there, Stephanie, but they've lifted it. I'm trying to control my cursor here, but they've lifted it off of the bottom just a little bit, which is really helping to minimize that heat by conduction as well. So using their science knowledge to say, oh, I didn't think about that, right, and I can come up with a better design. Do you want me to talk through this one, Stephanie?
Go for it.
I have the advantage over Stephanie here because I was teaching this class of students, so I know exactly what they were doing. So this was actually a group of middle school students, so they were aged around about 12 years old that were doing these. So in that second example, there's a couple of changes that they've made. First, they had just a big empty box, and that's a really large airspace, and that can cause problems with convection. And they also don't have a lot of insulation on that box. It's just looks like it's pretty much a piece of, it might be foam, it might be cardboard there. And so one of the changes they've made is to add more insulation. They've used the cotton ball to add more insulation onto the inside. The other thing that they noticed is this piece here, that it was sort of a sort of shiny umbrella that went over the top, was helping with radiation from the top. So it was helping a little bit to prevent radiation. But what they hadn't thought about is, if you remember, the cooker is lined with aluminum foil. So that light of the radiation is also hitting the sides of the box. And so one of the changes that they've made in this design is they've actually put, looks like they switched to Mylar actually, but they've got that reflective material all the way around the box. So they're doing a better job in their second design of stopping that radiative heat transfer as well. So we really have the students dig deep, thinking about what worked, what didn't work. And as Stephanie said, when they see the class data, right, they're able to say, oh, wow, well, why did this group do so well? Right, and borrow some ideas, right? And always having them think about those science vocabulary words as they talk about what they changed. Right, so we would ask them to say, "We changed this because," right, which Stephanie modeled with the use of the why use certain materials in the activity that you did as well. So sorry to jump in there, Stephanie. I just know lots about these pictures. So, but all right, I'm gonna keep going because I'm conscious of time. We've got about half an hour left, and so I want to share a few things, and I do want to try and leave some time for questions as well. So what I want to do is think a little bit with you about what are the benefits of teaching heat transfer using an engineering design challenge. So why would we think about teaching this way? And I'll bring us back to some of the frameworks that I shared last week when we were together. All right. So because the biggest question that we get from teachers is, well, this is going to take a long time to do this, right? To have students actually do this and build it and rebuild. Is it worth the extra time? right, to for students to do this, right? So one of the frameworks that I shared with you last week was these 6 characteristics of high quality integrated STEM curriculum. So I'll just talk briefly through those. So we know that for good integrated STEM, we need a meaningful, motivating, and engaging context. Kids love animals, right? They're excited about thinking about penguins and how they can help penguins. So this is a way that they can be more interested and engaged in learning that science, all right? We did the curriculum as an engineer and design task, right? And you got a little window into this, right? Stephanie had you working for 20 minutes in your group, and you had to do a lot of problem solving, a lot of thinking about content, a lot of creativity, right? To come up with these designs. That opportunity to learn from failure and redesign. You didn't have a chance to do that, but that last slide that we showed is to see how those designs improved when we gave the students a second chance to redesign, right? That yes, it didn't work great the first time, but I can use that new knowledge to do better the next time, just like engineers do in the real world, right? They don't get it right the first time. They have to keep iteratively improving that design. The fourth is that application of science and mathematics contents, right? So really understanding things like conduction help the students to say, oh, I need to lift this off of the floor a little bit. So making sure that there are opportunities to use that science knowledge in the design and use it to explain the design is really, really important. Teaching with student-centered pedagogies, right? If we just tell them how to build the design, students don't have a chance to engage in critical thinking, creativity. They don't have a chance to show us how they understand heat transfer. So letting them struggle and have agency in their own design decisions is really, really important. And then last, but definitely not least, promoting those 21st century skills, right? Which is connected to that open-endedness, that they're able to think creatively. You each had different designs, right? So there's an opportunity for creative and critical thinking there. All right, I'll also look back at the other framework that I shared with you, which had these 7 characteristics, and just talk about a few of them and why they're important to think about. So I won't talk about all of them because that would take quite a while. All right, but just to remind us from where we started last week, why do we do this, right? We're really interested in getting more students interested in becoming scientists and engineers. We want more students to pursue degrees in these STEM fields, right? And so by having a motivated context that students are more like, wow, I actually do want to learn about heat transfer. I want to know how to save penguins. I'm interested in how I might use science to improve the world, those kinds of ideas, right? So what our research shows us is by using these real world problems and these engineering design challenges, we do get students more interested in science, and we're starting to slowly see more students choosing STEM as a possible career route. But when we think about this, we have to really think about the kinds of challenges we pick. So if I go back to this slide quickly, if you remember from last week, when we think about who ends up going into STEM careers, it's not equal across gender or equal across race, right? So one of the statistics I shared last week that only 12% of engineers are women. All right. So when we think about the problems that we pick, we want to think about gender when we do that. So a lot of the STEM problems that we do have a very technical orientation. Can we build the fastest car? Can we build the tallest building? Those kinds of things. Those are very male-oriented things, right? Those attract men to the profession. But we know we want to attract more women. And so we want to think about real-world problems that have more of a communal orientation. So things like alternative energy, sustainability, medicine, things that are going to help people in the community. They're going to save people's lives, save the planet. Those kinds of problems are far more motivating for our female students. And so we want to find a balance there. So when we're picking problems, that we have that idea that, oh, well, if I'm an engineer, I can help save the world, right? Not just make the fastest car because I can, all right? So thinking about saving penguins, that really helps students to feel more motivated about the environment and then become more interested in the technical aspects of engineering. When we think about integration, right, it's really important that students need to know the science to solve the problem. and that the problem can't be solved just by tinkering. All right, so the example I have here, we have a lot of curriculum that we see where students are asked to build some kind of vehicle, right, that they can propel as a mousetrap car, different things like that. And what often ends up happening, because we use cheap materials, is they'll spend a whole hour just kind of tinkering and playing with that axle so they can make the car go in a straight line. But all they're doing is just kind of fidgeting around with it. They're not really applying science. So we want to make sure, just like in Save the Penguins, that students can apply that scientific knowledge. They need to know the science to be able to solve the problem. And we help do that by something we call evidence-based reasoning. And Stephanie modeled that for you, right? She asked you when you were designing your first prototype to say, I chose to use aluminum foil because it helps to reduce heat transfer by radiation, right? I chose to lift my design off of the floor to prevent heat transfer by conduction, right? We ask the students to formally use those contents and explain to us and show us that they understand that scientific content and how they're using that content in their designs. We talked about this a little bit already, but right, our real world problems are complex, right? There is no one single solution to how we could save the penguins. There are many different possible solutions. And because of that, that means that students have to use 21st century skills. You have to be creative. You have to use critical thinking to decide between the different options that you have. So using those real world problems opens up that problem space quite a bit. And that's tied again to students having agency in making their own design decisions. It's really, really important that students get to make the decisions, and we make it open-ended and student-centered. All right, really, really critical. Again, it takes longer, but it's worth it for those 21st century skills that those students are going to gain. And then last but not least, I mentioned this as well in an earlier slide, is we want our students to learn to celebrate failure. It is okay that we don't have the perfect design the first time that we do it. That's how engineers work, right? As engineers work, things don't work properly. They learn something from those mistakes and they use that new knowledge to innovate and improve their design. All right, so students need to be comfortable with failure, because if we can't be comfortable with failure, we're not going to be able to be innovative and become fruitful engineers, right? It's a difficult skill and habit of mind for students to learn. All right, and then one of the things we didn't model in this curriculum is STEM careers, right? And helping students understand that the work that they're doing, right, the work that Stephanie had you do, is the genuine work of real engineers, all right? And just as one example, and I won't play the YouTube video, but I will share the slides and the link is in there. This is a short YouTube video that introduces a civil engineer. Her name's Jennifer Nakayama. And as a civil engineer, her job, she works at SeaWorld in California. And her job is actually to help support the animals there in SeaWorld. And one of the jobs that she talks about in this YouTube video is designing habitats for the penguins that live in SeaWorld. Because they're in a warmer climate in California, which is not their normal climate. So they really have to think about keeping the penguins comfortable. And so as a civil engineer, that's actually her job. What a cool job to have, right? So that's really engaging for the students to think about the possibilities. And then I'll just share these slides. This is from, I had the opportunity to be in Australia a couple of weeks ago. I was there for a conference and then working with some students in Melbourne, some of their pre-service teachers around some ideas with STEM. They had the luxury of having me in person, which was nice. But we also had the opportunity to visit Phillip Island, which is on the south coast of Australia. So similar to the penguins that on Boulder Beach. And these are some actual habitats. These are pictures I took. These are our penguin habitats that the naturalists and ecologists have helped support that penguin colony. And put them there, and you kind of can see a little bit, but they also use the natural environment. So as they put these habitats, they then allow the soil and the grass to grow back over there, which helps with a natural insulation. So instead of using aluminum foil and bubble wrap and things, they're actually using natural insulation of soil and plants there as well. So there's some easy ways that you can think about just adding in a little bit about careers. Again, letting students think about, well, what might it be like to be an engineer? What kinds of engineers are there? Those kinds of things. So, all right, I just talked a lot. And so I wanted to put our emails up. We're happy to chat with you and stuff as you have more questions. But I'll stop sharing my slides and allow for an opportunity for people to ask questions as well before we close up, for us to go to bed and for you to carry on with your day. So.
Okay, thank you for the interesting presentation, both from Professor Gillian and Stephanie. Is there anybody here who want to ask to our speaker? Please raise your hand. Okay, Pak Aziz, please come here.
Hello, Prof. Roehrig. Hello, Stephanie. I am Aziz from Science Department, Science Education Department. I want to ask you a question. So, I have no doubt that STEM has an ability to improve creativity, collaboration, and many more. But in education, there are a lot of issues that I concerned about trust issue. I mean, how parents believe to teacher. You know what I mean? So when student come to school, I think teacher will do something like they will teach student better and better and do their best, especially through STEM approach like this. But when the student go back home, the parent doesn't care about that. And my question is how to maintain what students have got in school until they back home and then come to school again.
Mm-hmm.
Yeah, you know what I mean? I think.
Yeah, I think so. So I'll say a few things. You can tell me if I'm going in a different direction. But and Stephanie and I were actually talking about it a little bit with Stephanie's experiences in Nepal and other places we've been, and it's also true here in the United States. Is we're worried about the exams, right? Parents want the students to be ready, right, to be successful in those exams, go to college, all of those kinds of things, and until we're able to change the way we do testing, sometimes it's difficult, right, as a teacher to make space to do this in our curriculum, because the parents want to know, well, you should be teaching our students these things, right? Like it's school the way they're used to. It takes a lot of time to help parents understand that, and it's very slow and steady, right, in terms of doing that. So I certainly would not change my entire curriculum, right, as a teacher in Indonesia to do all STEM all the time, right? Still going to do some of those traditional things, but take a little bit of time, right, to do some of these more open-ended activities, right? Because there is a tension, right, between what parents experienced, what the test looks like, and then what we know is best pedagogy for our students. Stephanie, is that something that you grapple with in your classroom, with parents not understanding why you do things the way you do?
Parents and sometimes students. I think my students get frustrated too because they just want to know what the right answer is, and they just want to know, well, what am I supposed to do? Just tell me what I need to do so I could pass, especially with my older students who really, for some of them, they just wanted to pass so they can get their high school diploma. So it was a struggle with the parents, but also the students. But, you know, sometimes I would just try to prove to them through tests or through like having their student talk to them about their project that they are learning this a lot deeper and they can understand these words a lot better. So Like on parent night, I'd have the students present their project and have the parent hear them actually enthusiastically talking about and using science vocabulary. And that helped with a few of the parents too. And like Jill said, it is a slow process, and you don't want to completely do this overnight because it does take some change and factors outside of your classroom as well about how we test and how we evaluate students and their college readiness in science.
Okay, thank you for the answer. Is it clear, Pak Aziz? Okay, it's clear. Thank you for the answer. Is there anybody here? Okay, please.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Okay, good evening, Professor. My name is Amar. I am a teacher from Junior High School of Alabidin, Surakarta. I want to ask you a question about we as a teacher, we have one main problem about STEM, and it's time. Yeah, we have a very limited time, but we have a very much chapter that we need to deliver to our student. So I want to ask you about, maybe you can give us some, some example, some real example. For example, you can, give us timeline. How much time do you need to teach a student about one project? Yeah, and how much project you usually teach your student in one semester? Yeah, and maybe if you can give us more, you can maybe give us some, guideline from us teacher. It will help us so much. Thank you very much.
Yeah, that's time is our biggest enemy. Absolutely, in a lot of different ways. And it does take longer to do this, right? I can teach heat transfer in maybe 2 days. I could do the science experiments that we did, insulation, conduction, convection, and not do the engineering design challenge, right? These are choices we have to make as teachers all of the time. So I don't do engineering with everything I teach. You can't, there's not enough time to do that. So it's picking occasional times when we do this. So in my classroom, when I was a high school teacher, I would do something like this once a quarter, so 2 times a semester, roughly, to do that. There are also ways that you can bring in engineering ideas that take less time. So what we modeled for you was a full engineering design cycle. We went through the problem, we did the science, we designed it, we tested it, we redesigned it, right? That takes a long time to do that. But there are other ways. I'm actually going to share an example. So I'm teaching a class right now, and my students are doing their final presentations next week. And the chemistry teachers had an example around ocean acidification. And so they just added a real world problem of increasing amounts of carbon dioxide and how that's causing problems in the ocean. They were teaching about acidity anyway. And so to add this extra connection to the real world and ocean acidification, it only took them 1 extra day to do this. They were able to have the students think about and apply what they'd learned and discuss possible ways to change or reverse ocean acidification. They didn't build something, they didn't go through that process, but they were able to talk about and discuss what they might do. So that was a way to do a STEM lesson and just add 1 extra day and not a full set of engineering lessons. So Stephanie, do you want to add from your perspective how often you might do this in your classroom?
Yeah, it's a similar timeline in that I would probably do a full engineering design cycle over a school year, maybe once or twice. And I did one of my favorite units that I designed. The way I solved the time issue is I looked for a science lab that is pretty much done across the United States on work and power, where we have students walk and run upstairs and they have to calculate how much work they do and how much power they generate. I took that lab out completely and I just threw it away. And I said, instead of that, we are going to calculate how much work and power you generate in this alternative energy. And this alternative energy was water power. Everything else in my unit stayed the same. The teaching them how to do calculations, teaching them the physics of work and the physics of power, all pretty much I kept those the same. I just got rid of a lab and replaced it with a small amount of time for building. I really didn't give them a lot of time. I said, you have 20 minutes to build a water wheel, and then we're going to test it. And then I gave them another time at the end of the unit to do the same thing after they learned a little bit about work and power. But everything else was my same lessons that I had done for years. So sometimes looking for those things that maybe can be swapped out, where, you know, this is going to be better than this lab that I've done for 20 years or 10 years. That's where I found some time too.
And even if each teacher does one lesson like this each year over a student's time in school, they'll have had, what, 10 or 12 experiences with this, right? So if everyone does it once, that's a really big change for those students as they go across all of their schooling.
Okay, thank you for the answer. We have one question from the lecturer here.
Thank you for the opportunity. May I ask you questions? Where is the STEM assessment carried out? And can you give an example to the assessment? Maybe you have an article about that. Thank you.
So the assessment is in a lot of different places. So some of it is an ongoing assessment as the students are working. So we have our students keep an engineering notebook. So they'll have their different designs, and we might look at that notebook at how their designs are improving over time. So there's a lot of that kind of assessment that happens. The more formal assessment is at the end, when we are, so I had that slide where I had the before and after, right? First design, second design. That's the more formal part where they're going to explain how they improve their design. They're going to use their science words, right? I added mylar to prevent radiation, right? We're looking there and assessing their ability to use the science to make engineering decisions, right? So we can have some formal assessments that way, which works pretty well in the classroom. And students can write, it's almost like writing a lab report, right? That they can explain their design decisions. On the more external part, right? So the tests that all students take, right? Like sort of their national test, if you will. They're done by state, but so for us, a state level test. At Minnesota, we're starting to see test questions that ask students to do design thinking and to apply science. So we're starting to get some small changes in our state tests as well, which is really helpful for that piece. Again, talking about parents, right? What's the expectation? How do you do well on that test? We're starting to see a little bit of that. So in terms of papers, I've got some papers on evidence-based reasoning that I'd be happy to get together and share. And there may be some release test items that are engineering. I'm not sure. I'd have to look for those. So Stephanie, do you want to add how you assess from your classroom as well?
Yeah, I do a lot of the evidence-based reasoning, either with an engineering design, or if I'm not even doing engineering design, if it's an experiment. I also really am grading that evidence-based reasoning and I am very clear about these are the science concepts I need you explaining, and I'm having them write in their own words, explaining those science concepts. And I will give them word banks, like list of words, like you need to use these words and explain them well. And And I do still do a traditional paper, what we call paper pencil tests. So usually for every unit, I will have a kind of project or evidence-based reasoning assignment, and then I will also have a test. And both of those together I use to assess their understanding. So this is, a personal preference. I don't throw out the traditional tests completely. I still feel like those are important, and I can get at some of those knowledge things that we do need kids to memorize. I can get at those things through the test fairly quickly. And that is what I spend most of my time as a classroom teacher on. And then if I'm doing my job right, then they should do well on those state exams, because I am focusing their attention on and what the state has told me that I needed to teach. And it's worked out fairly well for me to have both pieces.
I think that's a really important point, Stephanie, is to say we're not saying you should completely change everything you do, right? It's still important that students can solve F equals MA problems. They can balance chemical reactions. They know the chemical symbol for sodium. All of those things are still important, right? So it's changing a small piece, not everything. I think it's a really, really good point, Stephanie.
Okay, and then the question from the student, one of the students, please, the last question. Is there anybody here want to ask? This is the last question in this session and this year workshop, I believe. Ya, dalam bahasa Indonesia tidak apa-apa. Yang kemarin mau tanya, tapi tidak ada waktunya, yang dari grupnya Bu Ica, kalau tidak salah kemarin ada. Okay, we don't have more questions today.
That's okay. No problem. And like I said, if there are questions that people want to ask later, we are happy for anybody to email us, and we're happy to help. So,
thank you. We are in the end of the presentation session. As the appreciation for all of the presenter, for the host, please show the certificate of appreciation.
Cool.
This one is Professor Gillian Roehrig, and then Miss Elizabeth Stretch. And the last one is for Miss Stephanie Erickson.
Thank you so much.
Thank you for coming and sharing many knowledge to us and your experiences. We think that it is helpful for us to give more insight about STEM, because STEM is still developing here. And we hope that we can collaborate in the near future in more interesting projects.
We'll be excited to continue to work with you. So thank you.
Thank you.
Thank you.
Okay. Yeah, this is the end of the session of the presentation.
Good night, everybody.
You may. Goodbye. Thank you for coming. Okay, Miss Shalom, time is yours.
Okay, thank you, Ms. Febriani Sarwenda, for leading the session. Also, I would like to thank you and highest appreciation to all of the participants and our speakers that joined this workshop from beginning to the end. We hope that the knowledge and insights we gain will be useful for all of us, especially for the future teachers. These are all of the agendas we have presented to you as we have finished our event. Thank you for your participation. It's been our pleasure to host this workshop. Please forgive me for any mistakes in presenting this event. See you all at the next event.